Hey, welcome everybody to our webcast where we're going to be talking about H.323 Gateways. And I titled this webcast the quote-unquote toughest topic on the CLCOR exam. And the reason I say that, I think the configuration of an H.323 gateway really is the toughest topic for many exam candidates because there are just so many steps involved. You've got to create voice classes. We've got to bind H.323 to an interface. We've got to set up the T1 or the E1 ports. We've got to set up our PRI group. There's a lot to do. We've got to set up all the ISDN parameters. And we're going to take you step by step through all that today. And we're going to give you the theory of CLCOR's H.323 topic that you need to know for that exam. By the way, my name is Kevin Wallace, if you're not familiar with me, and we are going to be spending, I'm just guessing, maybe about an hour and a half together today going through these topics. Here is the specific agenda that we're going to be going through. I want to start off by talking about what do we have in addition to H.323, what options do we have for communicating between a Cisco Unified Communications Manager and a gateway, a Cisco iOS router probably, that's going to get us out to the rest of the world. And by the rest of the world, I'm talking about the PSTN, the Public Switched Telephone Network. That's the public telephone network that we use when we call somebody pretty much anywhere in the world. We want to talk about how we communicate with that gateway that's going to get us there. And focused on the CLCOR exam topics specifically, we're going to take a look at some digital circuits. The CLCOR exam says we need to know about E1s, T1s, ISDN, PRI, BRI. We're going to configure for you today, probably the most common of those. We want to configure a T1 circuit, common in the United States or in North America and in Japan, and we want to configure that as a PRI interface to get us out to what we're going to have as a PSTN simulator in our environment. And the way that T1s work, we're going to be talking about the theory of this. We're going to talk about TDM. You hear that term a lot in telephony. That stands for time division multiplexing, where different conversations get their own time slot. They get their own, they take turns basically in communicating. So we can have all these different time slots take turns in communicating on this single digital circuit. And when we group those voice frames together, we don't send out just one frame at a time typically. We're going to see that a frame is 193 bits in length. We don't send out just one frame. We group them together in either a super frame or an extended super frame. That's in the T1 world, and we'll take a look at why we might want to do one or the other. And we also want to be able to represent ones and zeros where the other end's going to understand what we're saying with our ones and zeros, our binary communication. And the way we're going to do that is through a different type of line coding, AMI, B8ZS, HDB3. We'll talk about all of those today. And we'll talk about the different flavors of ISDN. ISDN, that stands for Integrated Services Digital Network. Now, when I first came across ISDN, I was working for a telephone company. It was GTE Laboratories back in the late 80s. And back in those days, some people referred to ISDN as I still don't need it because it had so much bandwidth. We thought at the time, I mean, a BRI circuit had like a whopping 128 kilobits per second of bandwidth. Who needs that? Keeping in mind that 1989 was before the World Wide Web, before browsers became available. So yeah, there wasn't a huge demand for it when it came to data. It was used a lot for voice, and it still is today. Then we're going to take a break. And if you're joining us here live during the webcast, something I always like to do for the webcast attendees is give you a special discount on some of our products. So we're going to be talking about the CLCOR video training series that we just released just a few days ago. And I want to give you a really big incentive and some bonuses for that if you're joining us live. If you're watching this on the replay on YouTube, since you're not joining us live, that section is going to be cut out. So I'll just edit that out before putting that on YouTube. But hey, if you're here with us live, be sure and stay tuned for the break. And if you want to ask questions, if you're in the live interface, go ahead and chat that into the interface. We're coming to you through our own kwtrain.com website. We're coming to you through YouTube and LinkedIn and Facebook all simultaneously. So I'll be monitoring the chat interfaces in the background and answering your questions as they come in. Then, after we talk about the theory of T1s, E1s, H.323 gateways, we're going to get into the configuration. We're going to go out to a Cisco 2900 series router, an ISR second generation router, ISR2. And we're going to give the command that's going to tell us what kind of hardware do we have in that router. And we're going to see that we've got a voice card that's going to give us the ability to be either a T1 port or an E1 port, and we're going to configure it for E1, or rather T1 in our case. We're going to configure it for T1 operation. We're going to say, I don't want you to just be a T1 circuit. I want you to behave as an ISDN primary rate interface, a PRI circuit, and we'll configure that. Then we're going to bind H.323 to a router interface, because that router interface, that gives us our IP address that's going to be used to communicate between the router and our communications manager server. And then we're going to take a look at how to configure some voice classes. And again, this is based on the CLCOR blueprint. And we're going to configure a voice class to adjust timers, because here in our environment, I've got two communication manager servers running. We've got one that we register with primarily, and we've got a backup. How long is it going to take to fail over from the primary to the backup in case the primary is not available? By default, it's too long. That failover timer is going to go beyond the timer for an ISDN circuit to be torn down. So we're going to be torn down before we ever get a chance to go to the backup. We're going to fix that with a voice class. We'll also use a voice class to say what codec, what coder decoder do we want to use for our communication. We'll give a list. We can prioritize a list of codecs that we can select from. And the way we add voice routing intelligence or call routing intelligence to a Cisco IOS router is through dial peers. We've got two types: POTS, P-O-T-S, which literally stands for plain old telephone service, as well as VoIP, VoIP dial peers. That's where we're going to be pointing to an IP address. With a POTS dial peer, we point to a voice port, like our T1 port is what we're going to be doing. We'll also set up some translation rules and profiles. We'll show you how that works, because we might want to do some digit manipulation when a call comes in from the PSTN, or maybe when it goes out to the PSTN. And we're going to take a look after we configure the router. We're going to go over to Cisco Unified Communications Manager, and we're going to add a gateway there, and we're going to add the call routing intelligence. We're going to set up a route pattern that will point to a group of phone numbers that I have on my PSTN simulator, and we're going to say, if you want to get to one of these numbers, go to this gateway, and this gateway is going to get you to one of those numbers. Then, and to make sure it all works, we're going to do a debug of an ISDN call. We're going to say, well, I'll save that for when we get to it, but we'll be able to debug the Q.931 protocol, and we'll be able to see the setup and the teardown of a call going out to our PSTN phone. Now, if you're not familiar with me, here's my super quick bio. Again, my name is Kevin Wallace. I've got a couple of CCIEs, one in enterprise infrastructure and one in collaboration. Collaboration is a big passion of mine, and I've been working with Cisco gear since about 1989. And I worked with the very first Cisco router back in the day, an old Cisco AGS Plus router, if anybody remembers one of those. I taught courses for Cisco Learning Partners for about 14 years, and then about 6 or 7 years ago, I decided to go into my own business and do this full time. Prior to that, I was a network design specialist at Walt Disney World. If you know anything about me, my family and I, we're huge Disney fans. And in a lot of our classes, I talk about some tales from the trenches from the times I experienced down at Disney World. And I've written a bunch of books. I've done a lot of videos for Cisco Press. I was honored to be a speaker at a couple of Cisco Live conventions and got the Distinguished Speaker Award both of those times. All that to say this: I'm passionate about Cisco technologies, and I cannot wait to spend about the next 90 minutes or so with you showing you how to configure an H.323 gateway. And one reason I'm particularly passionate about the CLCOR, that's the Collaboration Core exam, is my experience with voice and collaboration goes way back. I say that it's literally in my blood. No joke. This is a picture of me at 3 months. Let me get back to it. At 3 months of age. Here you see that I'm being held by my dad. He was a central office supervisor for the local GTE telephone company. So I grew up in and around a telephone office, and it's kind of a cool picture because you can see that my milk bottle is being warmed on a soldering iron in the background in one of the old GTE offices. If anybody knows about the old central offices, this was a step-by-step switch, or some people call it a Stroger switch. You hear all those clicking and clacking sounds. I can still hear that in my head. But yeah, I kind of grew up in this environment with telephony, and I absolutely love it. And I am thrilled to complete the CLCOR product that I just completed literally days ago. Let's see, what is today? March the 4th. Yeah, it's been just maybe a couple of weeks since I completed that CLCOR training course, and I've got to say, in my opinion, I've been creating training courses for two decades. In my opinion, because I'm so passionate about this topic, I really believe it's the best course I've ever done. The CLCOR course that just came out, it's the best course I have ever created, and you're going to kind of get a sampling of what some of that content is like today, beginning with the theory of Cisco IOS gateways. Let's put this in perspective. We're on our IP phone inside our enterprise, and we want to get out to the rest of the world. We want to get out to the PSTN. Well, the way we're going to do that is we're going to have some sort of a signaling protocol going on between our IP phone and the Cisco Unified Communications Manager, and we're wanting to get to this phone perhaps out there on the PSTN somewhere. Well, we're going to use a signaling protocol to tell the communications manager, hey, I want to call this phone out on the PSTN. Now, the signaling protocol I'm going to be using today is probably SIP, the Session Initiation Protocol. Some Cisco IP phones, some of the older phones specifically, they'll prefer to use the Skinny Client Control Protocol, or SCCP, and I just put it in here for completion. You'll probably never do this. Please don't do this. But it's technically possible to have an H.323 phone use H.323 to communicate with Communications Manager. You don't get many features like that. They basically just point to one another, and that's it. I would not use H.323 between the phone and the Communications Manager, but I list it because it's an option. You'll probably want to use SIP today. But when you're going from the Communications Manager to your router to the Cisco IOS gateway that gets you out to the PSTN, yeah, I'm a huge fan of using H.323 there. As we go out to the gateway and say, hey, we want to place a call to this phone number, and we're going to add call routing intelligence to that router today using voice over IP and POTS dial peers. The protocol that we're going to be using to communicate to that gateway, in our example, is going to be H.323, but a couple of other examples, you could use MGCP, you could use SIP, and we talk about all of those protocols in the CLCOR course, and we show you how to set up those protocols. And then the call goes out to the PSTN, the public switch telephone network, and then we've got bidirectional communication. The communications manager kind of steps out of the way and says, I'm not involved in this anymore. I got the call set up. I'll tear it down, but you guys just talk between yourselves. Again, our focus today is going to be on that H.323 protocol that's used between communications manager and our iOS gateway. And we're going to be doing that over a T1 circuit, or the T1 circuit's going to go from that gateway, I should say, out to the PSTN. And again, this is based on the CLCOR exam blueprint. So let's talk about digital circuits. Now, we know a digital circuit is going to communicate in ones and zeros. There's going to be a bandwidth amount associated with these circuits. And just as a reference, here are your different speeds for T1 and E1 circuits. We're going to be focused on a T1 circuit today, which runs at 1.544 megabits per second. If you have an E1 circuit, very common in Europe, the speed is 2.048 megabits per second. Now, this throws a lot of people. Does this seem confusing to you? It does to me. We think, okay, an E1 has more bandwidth than a T1, so the assumption might be that an E3 would have more bandwidth than a T3. That's not the case. As you see on screen, a T3 has 44.7 megabits per second throughput, which is more than an E3. Interesting. And even though our focus is going to be sending voice calls over these digital circuits, it's a digital circuit that you could use for data. I think I mentioned this earlier. T1s or T3s also, they're popular in North America and Japan. E1s and E3s, they're popular outside of North America and Japan. They're very popular in Europe. And if you're using these circuits for data, which you can do, you can have a T1 with 1.544 megabits per second of throughput. If you're using it for data, you probably want to encode it with some sort of a layer 2 protocol. The point-to-point protocol would be my personal choice. And you're going to be communicating with what you can think of as a digital modem, a CSU DSU. That stands for Channel Service Unit, Data Service Unit. But our focus is not going to be on the data aspect. It's going to be on sending voice calls. And to do that over this T1 circuit, we might have a bunch of conversations that need to go over this circuit. How do we simultaneously handle multiple conversations? Well, we're going to take turns. To paraphrase Whitney Houston, every conversation gets one moment in time. Literally, we're going to take this T1 circuit and chop it in to, here's a big number for your notes, we're going to chop it in to 24 channels. 24 time slices inside of that T1 circuit. And for the first time slice, we're going to have a voice sample from channel 1, the first voice conversation. We're going to send that voice sample. Then there's a time slice for the second voice call going on. We're going to take that voice sample, we'll send that over channel 2, and so on, all the way through channel 24. Or what we're going to do today, we're going to reserve channel 24 for a special purpose, signaling. And we're only going to send voice over the first 23 channels. But let's talk about where we get that number of 1.544 megabits per second. Let's do some calculations. We know that there are 24 channels in a T1. And this confused me for a long time because I knew that a single channel had 64K, 64 kilobits per second. That's called a DS0. That will send uncompressed voice. And I knew we had 24 channels, so I thought, okay, 24 times 64K, that should equal 1.544 meg, right? It doesn't. And it took me a long time to figure out what was missing. I want to show you what's missing. Yes, we do have 24 channels. Each voice sample is made up of 8 bits. And in our CLCOR course, we show you exactly where those 8 bits come from. What are they measuring? They're measuring the polarity, they're measuring the step value, or they're measuring the segment value. And they're using a logarithmic scale. They're using something like mu law or a law, a logarithmic scale. We get into that in the CLCOR course. But for now, just know that we can sample a voice wave by taking an 8-bit sample. How many samples do we need to take? Well, that's going to be dictated by something called the Nyquist theorem that we'll talk about in just a second. But here's the missing piece. Here's the reason my math was not working out correctly when I said 24 times 64K. Why doesn't it equal 1.544 meg? I was not considering the framing bit. There's a bit at the end of all these 24 time slots saying, all right, here's where the frame ends. If you include that, you suddenly have a 193-bit frame. Now, the Nyquist theorem says how many samples we should take per second. Harry Nyquist, back in the 1920s, he was a college professor. He worked at AT&T Bell Labs, or the predecessor to Bell Labs with AT&T. And he came up with the initial theorem, which was later developed and expanded on. But the Nyquist theorem basically says that if you want to take a sample of an analog waveform, like the spoken voice, you need to take twice as many samples as the highest frequency. Now, the human voice can have very high pitches or very deep frequencies as well. But it's really interesting that even though the human ear can hear up to about 20,000 hertz, 20,000 cycles per second, well, a young, healthy human ear, I listened to a little too much AC/DC in my time, probably when I was a teenager. So I don't quite hear it at 20 kilohertz. It's around 16 kilohertz for me. But over 90% of speech intelligence, the frequencies that allow us to understand what's being said, over 90% of those frequencies, they lie below 4,000 hertz. So in the voice world, generally, we're just trying to communicate below 4,000 hertz. So if that's our highest frequency, the Nyquist theorem says double that. 4,000 times 2 is 8,000. So let's do the math. I've got 8,000 samples per second. Each sample is 193 bits in length. That's 24 samples, 8 bits per sample, that's 192. We add a framing bit, that's 193. And you guessed it, 193 multiplied by 8,000, that gives us our 1.544 megabits per second. Now, when I say we're going to do framing, I'm saying we're grouping together these voice samples. A single frame is 193 bits, as we just saw. However, we don't send a frame by itself. They travel in groups, and those groups in the T1 world are either super frames or extended super frames. And there are two different types of signaling we might be doing: CAS, channel associated signaling, or CCS, common channel signaling. Let's talk about both for your notes. Channel associated signaling is not what we're going to do today. Channel associated signaling is where if we've got 24 slots, we're going to use all 24 slots to send different voice calls. We can have 24 voice calls because we're using each of those 24 channels for voice call. The challenge is, how do we send signaling information? How do we say, here's how we, or how do we say that a phone went off hook or a phone goes on hook? How do we send that signaling information? Well, we're going to use some framing bits. If we use a super frame, we're taking 12. Again, this is good for your notes. With a super frame, or SF, we're taking 12 of those 193-bit frames and we're kind of super gluing them together end to end. And then in that every sixth frame in a super frame, which is going to be frame number 6 and 12, we're going to go into the low order sampling bit for each of those 24 channels, and we're going to use that bit as a signaling bit. So with a super frame, each conversation, each of those 24 channels, it will have two signaling bits, an A bit and a B bit. And that's probably fine if we just have something like an analog phone, because it's on hook, it's off hook, there's not a lot going on. That's probably fine. And the way you might wonder, okay, how does an analog phone going off hook, how does that translate into ones and zeros? Well, if you're trying to support analog phones over a T1 circuit, what you'll often do is, and Cisco routers are doing this internally, but in the real world, you might see something called a channel bank. A channel bank is going to have, let's say, 24 analog ports where you can plug in phones or PBXs or things like that, your PSTN circuit. And then it's going to have an E1 port. And that channel bank is going to take that digital T1 port or an E1 port, and it's going to break it out into its constituent channels on analog ports. And when a phone goes off hook on channel 3, that's going to be represented by a couple of bits that are sent in every sixth framing bit using superframe. Or if you're connected to something like a PBX or something that needs more robust signaling than just on hook, off hook like a phone, you probably need more than an A and a B bit. You need 4 bits, an A, B, C, and D bit. That's what you get with what we normally use, which is ESF, extended superframe. We're still going into every sixth bit, or every sixth frame, and we're taking the low order sampling bit from each channel, and we're using those as the signaling bits for those channels. So each channel, each of our 24 channels in an extended superframe, they're going to get 4 bits, an A, B, C, and D bit used for signaling. Now that's with channel associated signaling. And while that will do some basic signaling, it's not very robust. You're not going to be able to look at those 4 bits and say, oh yeah, this came from HQ phone 1, and here's the bandwidth on the circuit, and here's the number that was done. You're not. It's basic signaling information. It's not very robust. You're not going to see why a call was torn down. There's not going to be that level of information. However, you can get that level of information by doing what we're going to set up today, and that's using common channel signaling. With common channel signaling, we're going to say, I'm going to take my T1 circuit with those 24 channels, and I'm going to send 23 voice calls across that T1 circuit. And with that 24th channel, I'm going to reserve it. I'm going to reserve it for sending a signaling protocol. That's what ISDN is going to do today. We're going to use signaling protocols. At layer 2, it's Q.921. At layer 3, it's Q.931. We're going to use those signaling protocols to send information out over our T1 circuit. And it's going to be very robust information, which we're going to show you later with a debug command. Now that's with a T1 circuit. How does an E1 circuit work? An E1 does not have the concept of a superframe or an extended superframe. An E1 circuit uses something called a multiframe. And a multiframe contains 16 frames, not 12 or 24, 16 frames. Now here's what I want you to put in your notes about an E1. A T1 we know has 24 channels. An E1 has 32 channels. So put that in your notes if you would. An E1 has 32 channels. However, 2 of those channels are reserved. The first channel, channel number 1, or channel 0, depending on where you start counting it, it varies in the configuration. But the first channel, whatever you want to call it, that is reserved for framing and synchronization. Because after all, this is a digital circuit. We need to do synchronization and know when one frame is starting and stopping. So it's reserved for framing and synchronization. The 17th time slot is reserved for signaling. Oh, does that mean we're just going to be using common channel signaling with an E1? Not exactly. Yes, there is a channel that is reserved for signaling. We're not going to be using that 17th channel to send voice. However, we can still do channel-associated signaling where we're sending 4 bits per channel. The A, B, C, and D bits, 4 bits per channel. Here's what happens. In that very first frame in this multi-frame, we have a series of bits in channel 17, and I hesitate to call it channel 17 because it depends where you start counting at 0 or 1. It depends if you count that first channel or not, but I'll say in the 17th channel, we're going to say, here is the beginning. It's like announcing, dum-da-dum, here is the beginning of a multi-frame. And then in the second frame in that multi-frame, in that 17th channel, we've got 8 bits. A voice sample is 8 bits, as we've said. So we're going to say, oh, we've got 8 bits. That's enough bits to send signaling information for 2 different channels. So I'm going to use 4 of those bits as the A, B, C, and D signaling bits for time slot number 2. I'm going to use the other 4 bits for time slot 18. Interesting. And then, as you might be able to guess, in that third frame, I'm going to send 4 bits as signaling information for channel 3 and 4 bits for signaling information for channel 19. And this continues all the way down until we have given 4 signaling bits for each of our 30 channels that are actually carrying the voice. Now that's channel associated signaling. And yes, you absolutely can do common channel signaling where you're using like an ISDN signaling protocol, and that's going to run in the 17th channel. So you can do either one. But remember, for your notes, on an E1, we have a multi-frame containing 16 frames. The first channel, or the first time slot in that multi-frame, that's going to be for framing and synchronization. And the 17th time slot, that's going to be for signaling, whether it's CAS or CCS. And since this is a digital circuit, we need to represent 1s and 0s on this circuit. How do we do that voltage-wise? Well, there are some options. One option is called AMI, and that stands for alternate mark inversion. And with AMI, the idea is the absence of voltage, or 0 volts, that's going to represent a binary 0. And the presence of voltage is going to represent a binary 1. So let's say that we're coming into this brand new byte, and we're currently at 0 volts. So that's a binary 0. Now, let's start our byte of 8 bits. And I need to send a binary 1. And I'll send it as a positive voltage. And then send a 0, so that's the absence of voltage. But now it's time to send another binary 1. Do I send another positive voltage? No. Here's the catch. We want to send an average of 0 volts on the wire. That's a good electrical characteristic, to have an average of 0 volts on the wire. So we'll send half of the binary ones as a positive voltage, and then we'll alternate those with negative voltages. So they're going to average out. The best metaphor that I've come up with is if I take one of my hands and I put it in a pot of freezing cold water, and I take my other hand and I put it in a pot of boiling hot water, on average, I'm going to be comfortable. Okay, that doesn't work for humans, but that is the way it works in these T1 and E1 circuits. We're going to have an average of 0 volts on the wire, and that's AMI. Pretty simple. There's a catch. The catch is, what if I had a byte that contains all zeros? In that case, it's like we're just hearing dead air basically for a while. How do we know when one byte is starting and stopping? There's really no intermediate voltage to say, oh, we must be on bit number 3. There can be errors that occur if you send with AMI. There can be errors that occur if you send a byte containing all zeros. Now, yes, there are some vendor proprietary solutions that make AMI work just fine. But in its raw form, you can have problems when sending a byte containing all zeros. So there are other options. One option that we see on a T1 circuit is called B8ZS. With B8ZS, that stands for bipolar 8-0 substitution. Kind of a big phrase. Here's what that means. This byte that you see on screen right now, it is a byte containing all zeros. You might say, hold on, I see some voltages in there. Yeah, notice what's happening. The voltage before we began this all zeros byte was a positive voltage. And at that 4th bit position inside of that byte, we're sending another positive voltage. That breaks the rules. We're trying to send an average of 0 volts on the wire. We just had what is called a bipolar violation. We've had 2 sequential positive voltages representing a binary 1. Well, to even that out, we'll immediately send a negative voltage, so that's going to average out to 0. And then a couple of bits later, we're going to do it again. We're going to have another bipolar violation. We've sent 2 negative voltages in a row, but again, to make it average out to 0 over this byte, we send another positive voltage. So we had 2 bipolar violations, but they occurred at very specific bit positions. And because they did, that's going to be interpreted by our equipment that's configured for B8ZS as saying, oh, that's code for that's a byte with all zeros in it. That's what that means. Now that's on a T1 circuit. On an E1 circuit, similar theory. It works a little bit differently. The polarity is a little bit different, but and the bit positions are different. But we also have a couple of bipolar violations with HDB3, which is high density bipolar of order 3. And I'll just leave that on screen there for a moment for your reference. But that's how we can send a byte containing all zeros. And when we configure our T1 circuit later, that's one of the parameters that we're going to be configuring. We're going to configure line coding, and we're going to configure B8ZS, which is the most common for a T1 circuit. Now, that T1 circuit could just be a T1 circuit. It doesn't necessarily have to run ISDN as its protocol, but that's what we want to do based on the CLCOR exam blueprint. Now, ISDN, Integrated Services Digital Network, we've got a couple of flavors of that. We've got a BRI, or a basic rate interface circuit, and we've got a PRI, a primary rate interface. Let's talk about both. First, a basic rate interface has 3 different channels. We've got a D channel, and for your notes, the D channel carries signaling information. It's running a couple of protocols. It's running Q.931 at layer 3 and Q.921 at layer 2. It's going to carry the signaling protocols for the other channels. And with the BRI, we've only got 2 bearer channels. These are the channels that we're going to be using to send voice calls or data. If we're using this for a data channel, we might bond those 2 together and use it for a 128K path because they're 64K each. Now in the voice world, we're going to use those 2 B channels, those 2 bearer channels as 2 separate voice channels. And since we've only got 2 channels, there's not a lot of signaling information that's needed for just 2 channels. So notice that the D channel, the signaling channel, it's only 16 bits in length, or only 16 kilobits rather in bandwidth. We're going to need a bigger D channel when it comes to a PRI circuit. Because with a PRI circuit, if it's based on a T1 based PRI circuit, that's going to have a D channel that is 64 kilobits in bandwidth, because it's going to be sending signaling information for 23 of our bare channels. So 23 bare channels. That's if it's T1 based, because remember, a T1 circuit, it's got 24 time slots, 24 channels. Well, we're now chopping this up into 23 channels carrying 23 voice calls, and then one channel carrying signaling information. But remember, an E1 circuit has 32 channels. One channel we don't even refer to here because it is reserved for framing and synchronization. And one channel is reserved for signaling. And with ISDN, that's that 17th channel, that's our D channel. And again, it's 64 kilobits in bandwidth. And it's going to be carrying signaling information for the remaining 30 bare channels, 64K each. So those are the different flavors of ISDN. And for your notes, I want you to know the signaling protocols that are going to be used. And at layer 2, it's Q.921. At layer 3, it is Q.931. So that, my friends, is an overview of the theory of H.323 signaling, signaling over to a gateway. We've talked about T1 circuits. We've talked about E1 circuits, ISDN, line coding, framing. We're about to set up an H.323 gateway, both on a Cisco router and a Communications Manager Express router. Before we jump into that, I do want to give a quick break for everybody that's joining us live here in the webcast. Hey, welcome back from the break, everyone. It's time to get into the actual hands-on configuration. Before the break, we talked about the theory of H.323 gateways. Let's set it up. Here is the topology that we're going to be working with. This is a topology that we build throughout the CLCOR video training series that we were talking about. We start out that series by seeing how to install a VMware ESXi server. That's our platform where we're going to install a bunch of virtual devices. We're going to install the HQ router. I'll show you how to download for free Cisco's CSR 1000V router. We set that up. We set up a virtual switch inside VMware ESXi. We set up a couple of Communications Manager servers, and we set up let's see, I've got an Active Directory server going here as well. We set up more than this. This is kind of what we have done when we get to the H.323 config. But what I want you to notice is I've got a couple of HQ phones. They're phones like this. These are the Cisco 8865 IP phones. So they got a little camera and a nice color display. Really cool phones. One of my favorite Cisco IP phones, actually. And they're at our HQ site, and we want them to be able to get out to the PSTN. So we're going to say that the phones at the HQ site, they belong to the 859 area code, and we're going to pretend that the office code is 222, and they use the last 4 digits for internal dialing. So we're going to have HQ phone 1 at 2001, HQ phone 2 at 2002, and we want to get out to the PSTN, and we're going to do that through a router, a 2900 series Cisco iOS router called HQ-GW for the HQ gateway. And it's going to use a T1 circuit to get us out to the PSTN. And at the end of this demonstration, hopefully, we're going to be able to call back and forth from an HQ phone out to this PSTN phone, which we're pretending has a phone number of area code 408, office code 333, and subscriber number 3001. So let's go out to the live interface, shall we? And I'm going to make this full screen. Right now it's a little bit small with my face on screen, so let me make this full screen so you can see it better, and we'll stay full screen through the demo. But here we're setting on that HQ gateway. And again, the goal is we want our Cisco IP phones at HQ to be able to get out to the PSTN, not just call within the local site. So we need some sort of a gateway to convert between the voice over IP world and the traditional telephony world, the PSTN. And based on the CLCOR blueprint, we're going to set up and configure an H.323 gateway to have an ISDN PRI connection on this HQ gateway that goes out to another router that I have configured as my lab PSTN gateway. And once we do that, we're going to confirm that a phone from HQ can call out to the PSTN, and the PSTN can call back in to our HQ phone. Let's see what T1 or E1 hardware we have in this router. Here's a command you might want to put in your notes. If I want to see what hardware I have, I'm going to say show inventory. And this shows me the cards that I have in my router. Now I want to draw your attention, let me highlight it for you, to this one. The VWIC1 MFT T1 E1. Now here's what that stands for. That stands for a voice WAN interface card, one multiplex trunk. That means this card has one port on it. And T1/E1 says this one port, it can be configured as either a T1 or an E1. You pick. Well, we're going to pick a T1. And when I'm doing that, I need to know how to address this card and this port. So notice it says we're in slot 0. Now on a 2900 series router, slot 0, that's the motherboard. So it's not in a module that we then plug into the router. It's its own little sub-module that plugs into one of the 4 open bays on the back of that router, and it's controlled by the motherboard. So slot 0, that's the motherboard. And I said there were 4 of those little slots in which we could insert cards. Well, the numbering starts at 0. It's 0 through 3, and I'm in sub-slot 0. So I'm in the first slot of those 4 available slots. And I've got one port and the numbering begins at 0. So my T1 port, and we'll see this later, my T1 port is actually going to be 0/0/0. The first 0 is the slot number. The second 0 is the sub-slot number. And the third 0, that is the number of the port. And I've only got one port. Numbering starts at 0. So let's configure this card as a T1 card. Let's go into global configuration mode. And I'm going to say card type T1 for the card that is controlled by slot 0, the motherboard, and is inserted into subslot 0. That's it. I've now transformed that card from a generic card into a T1 card. And notice we just had controller T1 0/0/0 come into the up state. Now, if we're going to configure this as an ISDN PRI connection, which is what we're going to do in this demonstration, we know we've got 24 channels available, but with an ISDN PRI, we're going to have 23 B channels or bare channels. Each of those can carry a voice call, and we're going to have one D channel. That's going to carry the signaling. Remember those 2 protocols? You put them in your notes. Q.921 signaling for layer 2, Q.931, that's our signaling protocol for layer 3. And if we did have our ISDN PRI circuit based on an E1, that would have 32 channels total, but that first channel, it's going to be used for framing and synchronization, and the 17th channel, that's going to be used for signaling, leaving us 30 channels for voice calls. And in the real world, you'll want to talk to your service provider and ask, what kind of ISDN switch do you have? Well, the way I have it set up in my lab, I'm using just kind of a generic North American ISDN switch type. I need to tell the router what kind of switch we're going to be talking to. I'll say ISDN switch type, and context sensitive help shows that we've got a few options. I'm just going with the national ISDN switch type for the US. I'll say primary, indicating a primary rate interface, primary-NI. Now, a T1 port, it is a synchronous port. That means we've got some clocking to say when one bit stops and another bit starts. So let's set up some clocking for this WAN interface card. I'm going to say network clock participate. I want the card in WIC slot 0 to participate in clocking. And what card, if I have multiple cards, what card is going to be the authoritative card for my clocking? I've only got one, so I'm going to specify that T1 port we just created. I'm going to say network clock select. I've only got one, so I can give it any priority number I want. I'll say it's T1 port 0/0/0, the only port I have. I didn't have much choice there. But this says we want the card in WIC slot 0 to participate in clocking over the network, and we're giving this port a priority 1 because we only have one port participating in clocking. Now, what we can do is go into this T1 controller and set up some parameters that we discussed earlier. Remember we talked about line coding? We talked about framing? Let's configure that. Let's go into controller, not interface, but controller T1 port 0/0/0. And we talked about line coding. We discussed AMI and B8ZS. Those were the options for a T1. We would have the option of HDB3 if we had set this up as an E1, but these are my options. I'm going to use B8ZS, bipolar 8-0 substitution. Remember, the two wrongs make a right with B8ZS. We can also set up framing. Are we going to group 12 of those 193-bit frames together? That would be a super frame, which would only give us A and B bits if we were doing channel-associated signaling. Or are we going to glue together 24 of those frames? That's what we want to do. ESF, extended super frame. The next thing we want to do is to group our B channels together, the bare channels. We want to group them together in what is called a PRI group. Now here's the catch. For your home lab, let me give you a little tip. The more channels you have participating in this PRI group, the more DSP resources you're going to need, the digital signal processor resources. And even though the router I have has plenty of DSP resources, it can handle all 23 of those channels, I want to show you how to set up a fractional T1, which might be useful in a home lab if you don't have a bunch of DSP resources. We're only going to, because this is all I need for the home lab, let's say I want to use 3 channels, 3B or 3 bare channels. I'm going to say PRI group time slots. Now, if I wanted to do the entire T1 circuit, I would say 1-23. But for a fractional T1, I just want to use the first 3 time slots. I'll say 1-3. And we'll press enter. And notice it creates, kind of on the fly, it creates those voice ports. We've now specified time slots 1 through 3. It's automatically going to include time slot 24. We didn't leave that out. It knows that we've got to include 24 because that's what's going to be used for signaling. And just like an Ethernet interface, we can make this controller administratively up or administratively down. Let's make sure it's up. I'm going to do a no shutdown. And here, I want to go into interface serial 0/0/0:23. Yes, the T1 port was controller T1 0/0/0. But if I want to go into the D channel itself, the signaling channel, I'm going to go into serial 0/0/0:23. Hold on. I thought 24 was the signaling channel. It is, but in the interface world, the numbering starts at 0. So 23 represents the 24th channel. And we want to make this act as an E1 bare channel, or excuse me, an E1D channel. And one thing I love to do is to make sure that we communicate all DNS and any information. That's another topic we talk about in the CLCOR course. For example, I want to be able to display on my phone's display who's calling. If a call comes into my phone and I redirect it out to a voicemail system somewhere, I want it to carry my phone number to the voicemail system. That's called the RDNS, the Redirected Dial Number Information Service. So the voicemail system knows what voicemail box to send the call to. Here's how I do that. I'm going to say ISDN outgoing display IE. The IE stands for information element. So I'm going to send my caller ID. Also, I'm going to say information element redirecting number. That's going to communicate my RDNS information to something like a voicemail system. And to make a router an H.323 gateway, we need to go into an interface and tell that interface, hey, you're in charge of speaking H.323 for this router. Now, I'm going to use the interface that connects into my HQ network in my lab topology. That's interface gig 0/0. I'll say interface gig 0/0. And to bind H.323 communication to this interface, I'm going to say H.323 gateway VoIP interface. And later, when I go into the communications manager server and point to an IP address, it's the IP address of this interface. And also, another reason I want to bind H.323 communication to this interface is if I happen to be sending information or sending voice packets from one IP address and receiving on another IP address, I mean, it's the same router, but I could run into a one-way audio issue. So to make sure that I'm binding all of my H.323 communication to this interface, I'm going to say H.323 Gateway VoIP bind source address, SRC-ADDR, source address 10.3.3.200. That's the interface's IP address. So let's enter that. So now we need to go in and set up some voice classes. And again, this is not necessarily a requirement. It's a best practice. And the reason I'm including it is based on the CLCOR exam blueprint. First, let's exit out of this, and I'll say voice class. And there are different types of voice classes I can create, several of them. I want to create two. I want to create an H.323 voice class, and I'm going to just give it a tag, a locally significant tag of a 1. Now, here's what I'm doing with this voice class. Imagine I'm getting a call that's coming into the HQ side. It's coming in from the PSTN. And I've got a couple of Cisco Unified Communication Manager servers. I've got a publisher, I've got a subscriber, great for backup purposes. However, let's say that call comes in and I try to extend it over to my subscriber, which is who we should probably use before the publisher. The publisher is busy doing publisher things. I try to send the call over to my subscriber, but for whatever reason, it's not available. Well, we want to set things up by having a secondary dial peer that if the subscriber doesn't answer, let's send it to the publisher. But there's an issue with that. When we do that, by default, the voice dial peers, they're going to wait about 15 seconds to fail over by default. So we're going to wait for 15 seconds for that subscriber to answer, and then we're going to say, I don't think it's going to answer. Let's try another one. Here's the problem. Not only is 15 seconds a really long time to set up a voice call, ISDN is going to tear down that circuit after about 10 seconds of not being completed. So you see the issue? Before we get a chance to fail over with our H.323 gateway configuration, ISDN is going to throw its hands up and say, I give up. It's going to tear it down. So I want to set that failover to a much lower value, like 2 seconds or let's do 3 seconds. I'm going to say H.225. Now that's the first H.323 is really a suite of protocols. One of those is H.225 that's used to start the setup of an H.323 connection, and that's followed by H.245. But for H.225, I want to say I want my timeout to establish a TCP session to be 3 seconds. And I'll apply that later to my dial peer. That's one voice class. Let's do another one. Let's create a voice class for a codec. And again, we give it a locally significant tag of 1. Now, this tag of 1 is not overlapping with that other tag of 1 that I gave to my H.323 voice class because they're different types of classes. They don't interfere with one another. Now, again, this is not a requirement, but this is going to give us more flexibility in allowing us to select a codec, a way of encoding our voice. And I would normally give a bunch of different options. I'll just give you a couple to keep the demonstration reasonably short. But I could go into a dial peer and say, use this codec. But if I do that, it's stuck to only using that codec. What if the other side doesn't support that codec? We're not going to set up a call. So what I can do is say, I want to support these codecs, and here are their preferences. I'm going to give the most preferred preference values a 1. I'm going to assign a preferred value to the codec of G711 mu-law, which there's not a Greek letter mu on my keyboard, so we use the letter U to represent mu. That's a G711 mu-law. That's uncompressed voice, common in the United States or North America. I'll also say, and I'll just give one more example. I would normally give G711 A-law and a bunch of others, G729, but just to show you how to do it, I'm going to just do 2. I'll say my second preference is to use ILBC. That's going to save bandwidth because G711, it takes up 64K payload only for a voice call. ILBC is a lot more bandwidth friendly, and it's great for using over something like a WAN connection. So now I've set up 2 voice classes as we're instructed that we need to know how to do based on the CLCOR blueprint. Now let's create some call routing intelligence. Let's create our very first dial peer. And this dial peer, the first one we create, is going to be for an incoming call. Call's coming in from the PSTN, so we want to match a call coming in over that T1 voice port destined not for an IP address. it's going to be a POTS dial pair, or a plain old telephone service dial pair. A voice over IP dial pair, it's going to point to an IP address. Here, we're not pointing to an IP address. We just want something to grab hold of that incoming call and do something very special with it. Here's how we set up a POTS dial pair. I'll say dial-pair voice. I'll give a locally significant tag of a 1, and it's a POTS dial pair as opposed to a voice over IP dial pair. And I want to make sure any call coming in from the PSTN is going to match this. Here's how I'll make sure we match it. I'm going to say incoming call-number. This is the DNIS. This is the number that was dialed that's coming into our gateway. The PSTN sent it to us. I want to match the number of dot. How does that work? Well, that dot is a meta character or a wildcard. That period, it represents a single dialed digit. And you might think, you mean somebody's dialing just one digit? They're dialing a complete phone number. Here's the thing. You might want to put this in your notes. Dial pairs use something called variable length matching. Now, what that means is if this call number or the dialed number coming in has at least one digit, ding, 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 we've got a match. If it has at least one digit, it's a match. It could have 12 digits. It'd still be a match because all we have to do to match this dial pair is to match one digit. Now, why are we trying so hard to match all incoming calls? So that we can give this next command. The next command is direct inward dial, DID, direct inward dial. What does that do? Well, by default, if you call into a voice port, you know what the router does? Gives you dial tone. Now, yes, from that dial tone, you could then dial the number that you want to reach within that site. But I don't know about you, but if I call in from the PSTN to a company and I'm presented with and I hear a dial tone, I'm going to think the call is terminated. I'm going to hang up and I'm going to try again until I just finally give up. Direct inward dial is going to suppress that dial tone that the gateway would normally present a caller, and it's going to forward the call based on the dialed number. Awesome. Now we need to set up a couple of voice over IP dial pairs that will get us over to our communication manager servers by pointing to the IP addresses of those servers. Now, because we're pointing to an IP address, that's why this is a voice over IP. This is a voice over IP dial pair. Now, let's set up, let's exit out of this, and let's say dial-pair voice to VoIP. And we'll press enter. Now, the destination pattern, that's the number that we're trying to match. Check out what we're going to do here. I'm going to say the destination pattern, destination-pattern is $2 ... $. Here's what's going on. We're going to dial, we're trying to match a pattern that is a 2 followed by any 3 digits. Now, the 2 phones I have at the headquarters, they're 2001 and 2002. What's up with the $? Well, remember the characteristics of variable length matching? By putting a $sign there, I'm saying that's it. There are no more digits. This is the end of the dial string. In fact, I could have put a caret symbol, shift 6 in front of the 2 to say this is the beginning of the dial string, but $2 ... $. So a dot represents a single dial digit. Let's now say where this is going to point. What's the IP address? Well, that's defined by the session target. It's an IP version for address, and my subscriber has an IP address of 10.3.3.2. So we'll enter that. Remember the 2 voice classes we created? Let's assign those to this dial pair. I'll say voice-class H.323. We're going to use that tag of 1, and voice class for the codec. We gave it also a tag of 1. We're now pointing to our subscriber's IP address with this dial pair, plus the 3-second voice class timeout that's applied, the codec selection voice class that's applied. Now, something else we want to do is set up DTMF relay. DTMF, that's when you dial a digit on your phone and you hear this tone, like on a regular analog phone, that DTMF, that's dual tone multi-frequency, when you press the number 5, for example, on your keypad, it's actually generating 2 simultaneous frequencies that will be detected by the switching equipment as, oh, they dialed a number 5 because they're sending these dual tones, these 2 different frequencies at the same time. Well, The reason we might want to set up DTMF relay is if we're using a codec that does compression, like G.729, for example, or maybe ILBC, those are designed for Latin-based speech patterns. They're not designed for music. They're not designed for tones. Bottom line is they could compress those DTMF tones to the point where they're not intelligible by the other side. So instead of encoding our dial digits with G.729, for example, which is going to do a big compression, let's send it a different way. Let's relay that DTMF information in a different way. What I can do is say DTMF relay, and we've got options. I want to use what I normally do on an H.323 gateway is I say H.245 alphanumeric. That's going to send these tones not as frequencies. It's going to send those tones as actual data, alphanumeric text, in other words. It'll be sent as data. Something else I like to turn off is voice activity detection. There's a common phrase in the industry that says VAD is bad. Voice activity detection bad. We generally don't like it. Now, it's got a good intention. It just doesn't do a very good job. The intent is to save bandwidth. VAD says if I don't hear anybody talking during this conversation, then I'm going to assume that I don't need to send any samples of voice. I don't want to send the sound of silence like Simon and Garfunkel would say. So I'm just going to send anything. Well, we're going to generate some generic background tone or background floor noise, if you will, but we're not going to send voice samples. The trouble is when somebody starts speaking again, it says, oh, so they started speaking again. I better start transmitting again. When it does that, it might clip off the first part of the first syllable of the word that was said. It's not a good thing. And we're not that concerned about bandwidth these days most of the time. So yeah, let's turn off that. We've created one dial pair, but for redundancy, I want to create another dial pair. Now, which dial pair do we use first? We're going to use the dial pair with the lowest preference value. Now, if I say preference, you're going to see the range is 0 through 10. Here's what I want you to put in your notes. The most preferred preference value for a dial pair is 0. The default is also 0. So I'm not going to put in a preference value for this dial pair because this is my preferred dial pair. I want to use this one. If the subscriber is available, I'm going to create another dial pair that will be used as a backup. I'll give it a preference value greater than 0. But this already has by default a preference value of 0. That is the most preferred. So I'm going to leave that alone. Let's create our second dial pair with a less preferred preference value. I'm going to say dial-pair voice 3, unique voice tag for that voice over IP dial pair. And I'm going to say the preference this time is 1, less preferred than a 0. Its destination pattern is going to be the same. I'm going to match a pattern of $$, saying that's the end of the dial string. And I'm going to say the session target is an IP version 4 address of 10.3.3.1. That's my publisher. I'm going to apply the voice class, the H.323 voice class of 1. I'm going to apply the codec voice class of 1 that we created. I'm going to set up DTMF relay for H.245 alphanumeric as we did before. I'm going to turn off VAD because VAD is bad. And I've now created my two dial pairs. I've added some call routing intelligence, but there's still a challenge. And that is when a number comes into my gateway, I'm not really sure what that dial number is going to look like. Is it coming from a local call that's sending me 7 digits? Is it coming from a long distance call that's sending me 10 digits? Does it have a country? I don't know what to expect when it comes in. I just want to pay attention to the last 4 digits. So what I can do is ignore all the leading digits and say, give me just the last 4 digits for this call based on just the last 4 digits. We can do that with something called a voice translation rule and a voice translation profile. Let's go back into global config. I'm going to say voice translation -rule. I'll give it a locally significant number of 1. And now I can create a bunch of rules within this translation rule. I can create 16 of them. And they're processed top down. And I'll say my first rule, and I'll just need 1 for this, is I want to take whatever comes in and I want to replace that with just the last 4 digits of what comes in. Now there are some meta characters involved here. And let me give you the basic syntax. We're going to have two sets of forward slashes. You see, I've got two sets. What goes in the first set of forward slashes is what I'm trying to match. What goes in the second set of forward slashes is what I'm going to replace it with. And there are a bunch of meta characters that you can memorize for the real world or have a reference, but let me show you what we need to do here. For the matching dial pattern in that first set of forward slashes, I'm going to say dot star. The dot represents a single dial digit. The star or the asterisk, it represents 0 or more occurrences of the previous meta character. In other words, that dot star could match just one digit. It could match 2 digits. It could match 12 digits. It's 0 or more occurrences of that previous dot. But we want to pay attention to the last 4 digits. How do I grab hold of just those last 4 digits? Well, I can put them in what is called a set. The way we create a set is to create a set of parentheses. I'm going to say in parentheses 2 $$ sign to say the $ says these are the last digits that are dialed in the dial string. I'm going to say if we match anything that ends in a 2 anything, that's going to be a match. But I want to create those last 4 digits in a set. And I said a set is going to be inside parentheses. There's a challenge with that. The parentheses is going to be seen as its own special character. So I need to negate the special character behavior of a parentheses. And the way I do that is I give a backslash. So I will say backslash open parentheses instead of just a parentheses. And then I'll say 2 $$ sign. And then I need to give a close parentheses. I'll give a backslash to negate the special meaning of that closed parentheses. I'll say close parentheses. And now I'm done with what I'm trying to match. So I'll close out that with a forward slash. So again, it's the pattern that we're matching followed by the replacement. The pattern that we're matching inside of this first set of forward slashes is dot star, which is 0 or more occurrences of a dot. So that could be 1 digit. It could be a bunch of digits. But then inside parentheses, we're saying 2 $$ sign. The $ says this string is ending in a 2 followed by any 3 digits. And because we're in parentheses, I can refer to that set. That is set number 1. If I had another set of parentheses, that would be set number 2. By the way, if I wanted to represent the entire matched string, that's set 0. That's a default set. But I just want what's in set 1. So my replacement, which is going to be in a set of forward slashes, remember, my replacement is going to be, give me what's in set 1. And the way I say give me set 1 is I do a \1. That's it. I close out my replacement with that closing forward slash. So see, we've got a set of forward slashes representing the number that we're matching, and another set of forward slashes representing what the replacement is. Match anything that ends in 2 $. Replace it with just the 2 $. That's what we want to do. That's what's going to match our voice over IP dial pairs. However, this rule, what exactly is it going to be translating? Is it translating the caller ID? Is it translating the number that was dialed, the DNS? Is it translating the redirected DNS? We got to specify that. And we do that with the voice translation profile. We've created our rule now, so let's exit out of that and let's create a voice translation profile. I'll say voice translation -profile, and I'm going to call it strip in uppercase because I'm stripping off the leading digits, and I like to generally use all uppercase when I'm naming something like this. That way, when I look through my config, if I see something in all uppercase, I think, oh yeah, that's probably something that I did. That's something that I came up with. So I want to translate the number that was dialed, the DNS, the called number. I want to translate that based on our voice translation rule that I created that I numbered 1. There's my voice translation profile. In order for that to take effect, I need to apply it to my T1 circuit, specifically to the D channel of my T1 circuit. Remember when we created that PRI group, it created all those virtual voice ports? I need to go into voice-port 0/0/0:23. Yes, the numbering starts at 0, so this is the D channel. This is the 24th channel. And in that D channel, I'm going to say, I want to apply the translation profile of, I need to say which direction do I want to apply it. Is the calls coming in or is the calls going out? I want to translate calls coming into this port using the voice translation profile that I've named strip. And we're done. I'll copy running configuration to startup configuration. We have now configured the H.323. Oh, actually, no, we haven't. There's one more thing. I don't want to forget this. This is kind of a big deal. What if I'm calling out to the PSTN? I've got to have a number that says, all right, you want to call somebody in the rest of the world? Go out this port. Go out this T1 port. So I need another POTS dial pair to match pretty much any dialed number and send it out that port to the PSTN. So let's create another dial pair. Almost forgot this one. Dial pair. I think we're up to number 4, and this is going to be a POTS dial pair. Oh, I forgot to say voice. Dial pair voice for POTS. And I want to match a destination pattern of dot capital T. What does that mean? The dot, as we know, represents any dialed digit. Oh, well, specifically numbers in the range of 0 through 9. In addition to the, well, actually, it'll also do the asterisk key. Now, the T key, or the T number there, or the T character, it matches any number of digits in the range of 0 through 32 digits. So a pattern of dot T, that's going to match one or more dial digits, followed by 0 or more dial digits. It's going to match pretty much anything. And when I match anything, that's going to go out of port 0/0/0:23. We're pointing to the D channel, and it's going to select an available bare channel in that T1 circuit. Now I'm done, and I'll do a copy run star. And we've set up our gateway now, but we now need to associate this gateway. I've already pointed over to my subscriber and my publisher. We need to go to our communications managers now and say, here's how to point to this gateway. And if you dial this number out on the PSTN, go to this gateway. So let's go over to our communication manager server now. I'll get logged in. Give it a moment to get us logged in here. And let's create a gateway. I'm going to go under device, gateway. I don't think I have any gateways right now. Let's find out. Let's do a find. No, let's add a new one. I'll say add new. And when you're adding an MGCP gateway, you need to be very specific about the type of Cisco router that you're using, because it needs to know the architecture of that router. Not true with the H.323 gateway. We just very generically say H.323 gateway. That's it. And we say next. It says, what is the device name? Well, we're going to point to its IP address because I don't have it set up with a DNS entry. 10.3.3.200. That's the IP address that we bound to H.323 communications. We also talk about dial pairs, classes of service in the CLCOR course, or the device pool. I've got one set up for HQ, and we show you that. We set that up in the CLCOR course. Now, something I do as a best practice, significant digits. I want to say 4. Now, yes, this is overkill. I admit it. I wanted to show you both ways of doing the same thing. Remember when we just created the voice translation rule and the voice translation profile? The CLCOR blueprint says we need to know how to do that. That says that voice translation profile said only pay attention to the last 4 digits. So does this. I can tell the gateway configuration screen without doing all that other work. I can say, yeah, just pay attention to the last 4 digits. That's what we consider to be significant digits. So 2 ways of doing the same thing. But even in the real world, I would prefer to do both, just kind of as a safety net. Calling search space, that says who is allowed to make a call. We want this gateway to be able to call and match a number at the HQ site. If I scroll down just a little bit, redirecting number, IE delivery inbound. That's going to help with our caller ID. Also want to say redirecting IE delivery outbound. I want to say display IE delivery. But check this out. There's an option here for enable inbound fast start, and there's an option for enable outbound fast start. What is fast start? Well, when we're setting up an H.323 call, there's a lot of back and forth communication that's used to set up that call. It begins with an H.225 message from the sender's side telling the receiver side, hey, I want to set up a call with you. Then the H.245 protocol kicks in and they go back and forth and they discuss things such as, hey, what codecs do you want to support? Or, okay, great, let's use this one. What about fax rates? What fax rates do you support? What number do you want to use for your RTP port number that carries voice? Now, there are a lot of these back and forth exchanges where the parameters of a phone call, they're decided on. But with Fast Start, it's a lot more efficient. Basically, with Fast Start, there's only one round trip. The originator says, I want to set up a call with you. Here's a list of codecs I support. Pick one. Here's a list of fax rates I support. Pick one. I'm going to be using this port number for RTP packets. What's yours? What number are you going to be using? And the other side responds. That's it. The call's set up. That's Fast Start. In order for it to work, though, both sides of the communication need to be enabled for Fast Start. So here's what I like to do. I like to check enable inbound Fast Start. That's going to make me compatible with a call that comes into me that wants to use Fast Start. So I'll be compatible with that. But I don't like to select enable outbound Fast Start, because if I do that, when I'm the originator, when I'm sending a call to somebody else, I don't want to force them to use Fast Start, because if they don't support it, the call's not going to be set up. So this is going to be my most compatible configuration. And let's save that. Now here's a gotcha for the real world. Even though I really believe I've set this up correctly, it probably will not work right now until I reset this gateway. So after I create a gateway, I like to reset it. There are so many times I think, what did I misconfigure? It was configured correctly. I just needed to reset it. Now I've got a gateway. I need to create a pattern that's going to match a number out on the PSTN that's going to point to this gateway. Now, yes, and we talk about this in the CLCOR course. We talk about the acronym of DLGP. We set up a device, a route group, a route list, and a route pattern. But here we're keeping it super simple. I'm going to create a route pattern that's going to point directly to this gateway. I'm going to go under call routing, route/hunt, route pattern. And actually, you know what? Just to make it a little bit more real world, let's not do that. I just changed my mind on the fly. I want to create a route group. This is the way you would typically do it. I don't want to show you a shortcut. I want to show you the way it's normally done. So in this route group, I don't think we have any. Let's see. Nope, we don't. Okay. Let's add a route group. A route group is going to contain a device. A device could be a gateway, like we just configured. It could be a trunk, like a SIP trunk. But here it's just going to be a gateway. So I'll say the route group name is HQ2 PSTN. And I want it to contain, see, I've got a couple of trunks already set up, CUC and presence. I want to add this gateway to the route group. So that gateway is now added to the route group. Let's save that. So remember the acronym of DGLP. Device, we configured first. That was the gateway. G, route group, we configure second. It contains the device. And notice that it says these are ordered by priority. Let's create a route list. GGLP. The L is the route list. I don't think I have one right now. Let's create one. And I'm going to name this route list. I'll just name it the same thing. It's not going to interfere. I'll say HQ-TO-PSTN. And I'm going to put it in a communications manager group for headquarters, and I'll save it. Once I save it, I get more options. Once I save it, I can say, all right, which route group goes here? I'm going to say the route group that goes here is this HQ to PSTN route group that I just set up. Now, I could do some digit manipulation here, and we talk about this in depth in the CLCOR course. I'm not going to do that here. I'm going to do my digit manipulation at the route pattern level. Let's save this, though. And let's make sure our list is saved. So we did D, we created a device, the gateway. G, we created a route group that contained the gateway. L, we created a route list that contains the route group. Now we do the P, the route pattern, that's going to point to the route list. We'll say route pattern. And we're going to use some wildcards again. Let's see if we have any. I don't think I do. Yeah, let's add a brand new one. Now, to get to the outside world, it's really common practice to dial a 9 to get an outside line. So I'll say 9 dot. Now, why am I doing the dot? Well, the 9 is my internal code within my company. That's the code for dialing an external number. It gets us an outside line. It gives us a secondary dial tone. That's what we're accustomed to. Even back in the PBX days, that's what we're accustomed to. Now, the dot is going to be used to discard that 9 because I don't want to send the 9 to the PSTN. It's going to say 9. I don't know what to do with that. So we're going to do what's called a pre-dot discard to say get rid of the 9 before we send it to the gateway. So we say 9 dot. And for a long distance call, which is what we're pretending this is, in North America, I'm going to dial a 1 because that's the North American country code. And within North America, we have a 3-digit area code. And there's a rule that the first digit in those 3 digits cannot be a 0, cannot be a 1. 0 gets you the operator, and 1 is the North American country code, so we don't use those. How do I say I want digits not including 0 or 1? In brackets, I'm going to give the allowable digits. 2-9, close brackets. I'm going to match any digit in the range of 2 through 9. And that's going to be followed by any 2 other digits. And those are capital X's. That's my area code. Now I'm going to do my office code. And in North America, we have a 3-digit office code. And again, the first of those digits cannot be a 0. It cannot be a 1. So in brackets, again, I'm going to say 2-9, close brackets. XX, that's my office code. And then we have a 4-digit subscriber number, XXXX. Awesome. What are we pointing to? Well, first of all, I need to put this in a partition to see who has permission to call it. I'll put it in the internal partition. We talk about partitions and calling search spaces in the CLCOR course in depth, of course. And I'll leave the provide outside dial tone selected. And I'm going to be pointing to the route list of HQ2 PSTN. Now, if I had not put the gateway inside of a route group, I would have had the gateway as an option. I could point at a route pattern. That's what I almost did at the beginning. Then I decided, now I'll give you the more real-world example. I could have pointed directly to the gateway. If there's only one way to get there, why go through all the process of creating the route group and the route list? But this is the full-blown way of doing it. So I'm pointing to that route list of HQ2 PSTN. Now, I want to get rid of that leading 9. I don't want that to be sent out. So I'm going to go under called party transformations, and I'm going to say I want to do a pre-dot discard. I'm going to do a pre-dot discard. Let's save that. And we'll say, okay. This should work if I've set everything up correctly, and if not, we can do some troubleshooting. So let me give you the topology again. Here's the topology. I'm going to go to HQ phone 1, and I'm going to dial 1. I'll dial a 9 to get an outside line. Then I'll dial 1-408-333-3001, and hopefully we're going to hear a phone ring, and I'm going to be connected to that phone call, or to that PSTN phone. Let's go place that phone call. Let's dial 9. We get an outside dial tone, 1-408-333-3001. We'll answer, and we'll hang up. Let's take a look at our debug output. Here's the number that we dialed, 1-408-333-3001. Notice that the 9 is not there that I dialed to get an outside line. That's because we told the route pattern to do a pre-dot discard. But something that's not awesome about this is the caller ID. 2001. That's what shows up on the PSTN's phone. It's caller ID display. I don't know about you, but if I'm on the PSTN and somebody calls me and it says I'm getting a call from 2001, that's a bit strange. I'm going to expect a more qualified phone number than that. There are different ways that we could fix this. We could use a voice translation rule and a voice translation profile, and we could manipulate it there, or we could simply go back to the route pattern. And under the calling party transformations, I can say, I want the calling party transform mask to be, let's see, let's make it a 1-859-222-XXXX. So whatever the 4 digits of the directory number are, that would be sent out, 2001 in my case, it's going to prepin the 1859222 to that. So let's do a save. Okay. Let's go place that very same call again. In fact, I'll just hit the redial button and we'll see what happens. All right, call went out. Look at this. The caller ID now looks a lot more intuitive than 2001. We now have a North American country code, we've got an area code, and we have the subscriber number. And that is a look at how to set up an H.323 gateway, both on Communications Manager and on a Cisco iOS router.